For part 2 of chapter 14 homework, we're given two questions where we're asked to calculate the Kb and the Ka for weak acids. And they approach both of these questions a little bit differently than we approach these in class. And so I'll help you work through these two questions here. So for question 1, they ask you, the unknown weak base, a concentration of 0.091 molar, and has a pH of 11.7. Just be careful that pH is a variable, so it might be different for you. And they ask what the pH of that base is. And so to begin with, calculating Kb is a little bit different because if we have a base, our general base is going to react with the water, our acid, to form the conjugate acid and the conjugate base. So our Kb expression, it's a little bit different than our Ka expression. It would be the concentration of our conjugate acid times the concentration of hydroxide all over the concentration of our base. They give us pH. So we have to do one step first before we can use those values to start to find some of these values in our Kb expression. So again, we start with pH, but we know we can turn pH into POH, and then we can turn POH into hydroxide. Once I know hydroxide, then I can start working with my Kb expression. So the first calculation, right, we know pH plus POH equals 14. So that means the POH of this solution equals 14 minus 11.7. So my POH equals something like 2.3. Step 2, now I can find my hydroxide concentration because I know hydroxide equals 10 to the negative POH. So hydroxide equals 10 to the negative 2.3. My hydroxide concentration at this pH ends up being 5.01 times 10 to the minus 3 molar. Now we can plug that into our Kb expression. So Kb equals my concentration. My conjugate acid and the base are formed in the same 1-to-1 ratio. So because I know my hydroxide concentration, I also know the concentration of my conjugate acid. Those two are equal. So I basically got 5.01 times 10 to the minus 3 times 5.01 times 10 to the minus 3. Here's where they handle this a little bit differently than we did in class. So basically in class at this point we said we can assume that the change in X is really small relative to the concentration of our acid, our base. We can ignore that. They don't ignore that change in concentration. So this is our initial concentration. We start with that much base, and basically because this is my concentration of hydroxide, that tells me how much of the base has ionized. So the one change they do differently is they basically say, okay, here's my initial concentration of that acid, or that base rather, and I know that 5.01 times 10 to the minus 3 of that ionizes. So they account for that change in concentration. So when we multiply those two together, we should get a Kb of something like 2.9 times 10 to the minus 4. Two significant figures because I've got two numbers after the decimal in my pH. If you did not account for this change, which probably you didn't because this is my mistake, right? We covered this in class and just said assume the change is negligible, don't worry about the change. you would have gotten a pH or a Kb, something like 2.76 times 10 to the minus 4. And so you can see they definitely are different values. I mean, I guess this would round to 2.8. They are different values, and part of that too is because of the concentration. This is a very low concentration, so yes, 5 times 10 to the minus 3 is closer to 0.09, 9 times 10 to the minus 2 molar. So that'll help you for this question. On the midterm exam, on the final exam, we're going to assume that this change in X is negligible, and we can ignore this extra step right here. For question 2 in chapter 14, part 2 homework, it's the same thing. It's a weak acid, and they ask for the Ka of that weak acid. This one's a little bit easier because we start with pH, and we know that Ka is the concentration of hydronium times the concentration of my conjugate base all over the concentration of my weak acid. They give us pH. We can turn pH into hydronium concentration, and then we can get to work finding the Ka. But we're going to find the same issue here, is that they account for that change in concentration. They don't use our initial concentration as our equilibrium concentration. So first things first, right? Hydronium concentration equals 10 to the negative 1.8, right? 10 to the negative pH. So my hydronium concentration for this is 1.58 times 10 to the minus 2. And you can already see, right, that's pretty close. Right, that's on the order of our concentration of our acid to begin with. So here, this change is big relative to our initial concentration of the acid. This also happens to be the concentration, right, of the conjugate base, because again, they're formed in the same 1-to-1 ratio. So now we can find our Ka. Right, Ka equals 1.58 times 10 to the minus 2 times 1.58 times 10 to the minus 2. And here's the difference, right? The difference is the questions we did in class. We just said, okay, here's my initial concentration that equals my equilibrium concentration. But we know that's not the case, because in order for this to reach equilibrium, right, some of that acid had to ionize. How much had to ionize? Right, 1.58 times 10 to the minus 2 of that acid ionized. So our initial concentration and our equilibrium concentration are not the same. And again, this is an issue because of how low this concentration is. If we were working at a much higher concentration, this wouldn't have as big of an impact. So we multiply those two together and divide, and we get a Ka of this weak acid of approximately 3.4 times 10 to the minus 3. Again, two significant figures because I have two numbers after the decimal in my pH of this weak acid. So hopefully that helps with these two homework problems. Like I said, for the practice exam and the midterm exam, the concentrations, the initial concentrations will be large enough that this change in concentration will be negligible. We won't have to worry about how much is lost to reach equilibrium.